Hello. In this video, we are going to take a look at polar equations. This is really just a review section to make sure that we're all familiar with the idea of polar coordinate system and polar equations. Ideally, this is something that you cover in a pre-calculus class, but it's one of those things that's towards the end that we don't always get to. So I want to make sure that we're all kind of comfortable with the system before we get into the calculus of polar equations in the next section. So we're going to just kind of practice graphing points, converting between polar and rectangular, and play around with some graphs in the polar coordinate system. So first, let's look at graphing in the polar coordinate system. Now, usually we use a grid more like this one, where I have circles, concentric circles, instead of a rectangular grid, like we would with the rectangular coordinate system. And my points are going to be a number and an angle here. The number is the radius, or the distance from the center of this polar coordinate system. So there's my origin, also called the pole in the polar coordinate system. And any point that I'm trying to describe in the system, this first number would be that distance between the pole and my point. And then pi over 2 would be the angle between this line here, also known as the positive x-axis. So the angle between this and the line that connects my point to the pole, that would be where that angle comes from. And so angles that are going to the left, just like in trig, that are going, counterclockwise, those are positive. And then clockwise is, so if they start by going down into that fourth quadrant, then that would be a negative angle. So we're going to play around with negatives and see how those are affected, whether they're in the radius or the angle. So first, let's graph just a simple one, 2 pi over 2. So the concentric circles are here to mark those radii because they're kind of hard to measure otherwise. So I would want to go out 2 circles to the second circle to get the right radius, and then I just have to find the right angle. And some of the angles are already drawn for us. For instance, 0, pi over 2 straight up, pi to the left, 3 pi over 2 going down. And then I have this split up into sixths here. So I can see 6 pi pieces on the top. So each one of these is going to be another pi over 6. So pi over 2 is straight up and 2 above the pole. So it looks something like this. For negative pi over 6, well, the negative on that angle means I'm going to go down instead of up, starting at the polar axis here, or positive x-axis is what we're used to looking at. And so going down 1, there's my negative pi over 2 would be this line here, and I'm going to go out 4 circles for the radius of 4. And there is 4 negative pi over 6. So those are not too bad. The tricky one is when the radius is negative. And so how I usually graph these is I start by ignoring the negative and I say, okay, where would this point be if that was a positive 3? So I'd have to go out 3 circles, and then I go out to 2 pi over 3. Now looking at this top half, pi over 6, here's pi over 3, or 2 pi over 6. And then we keep going. So 2 pi over 3 would be over here. This is 2/3 of the top half. So that would be 2 pi over 3. For the radius, when it's negative, I take this point now and I'm going to flip it over to the other side, or I can think of that as adding pi to it. So if I add pi to this, I'll end up down here, or you can just follow the line down if you've got a polar grid in front of you, and that will get me to negative 2 pi over 3. So not the easiest way to get to that point, which brings me to the point to note that these are not unique. With the rectangular coordinate system, if I give you an x and y coordinate, there's only one way to get to that point. There's only one x and y coordinate to describe that location. Here, though, because we have that periodic part to angles, I can just keep adding 2 pi and I'll get to the same point again. Or I could subtract 2 pi over and over again, and I'll get to the same point with a new set of coordinates. Or I can change the angle or the radius here to a positive or negative and change the coordinates. So they're not unique. It was just something to keep in mind with these. But again, this is not something I'm going to be testing you on in this course. It's just something I want you to be familiar with as we go forward. Okay, so the next thing that we want to be able to do is convert between polar and rectangular. And we're going to do this with points, but the same formulas apply for converting an entire equation from polar to rectangular or vice versa. So if I want to go from polar to rectangular, I can use trig identities. So cosine of theta is equal to x over r, and solving that would give me x equals r cosine theta. And same thing with sine, y over r, which would give me y equals r sine theta. Okay, again, I'm not going into how these formulas are derived really, but we're just focusing in this video on how to use them. The other one is tangent theta is equal to y over x, and x squared plus y squared equals r squared. So these are going to really connect an x and a y coordinate to an r and theta, or vice versa. So let's look at an example of each one of these. So let's say I want to take these polar coordinates 3 and 3 pi over 4, and I want to convert them to rectangular. So again, I'm going to be using these ones on the left, okay, because I have the r and the theta, and I want to get to the x and the y. So I'm going to plug in, r is going to be 3, theta is 3 pi over 4. So plugging that in to the formula for x, I get negative 3 root 2 over 2 for my x coordinate. And we do want to try and go with exact values whenever possible here. And then for the y, you just switch it to a sine function, and we get positive 3 root 2 over 2. So my coordinates, I can write an x, y coordinates as an ordered pair there. Now, if I want to go the other way, so rectangular coordinates, this one's a little bit trickier depending on which quadrant that you're working in. Something to keep in mind is that we're using that formula for tangent theta, and if you're using your calculator to plug in that tangent inverse and solving that, it's going to have a restricted domain. You're only going to be able to get values in the first and fourth quadrant when using your calculator. If you're using the unit circle, this is not an issue, but if you're using a calculator, you really want to pay attention here. I'm going to have to make adjustments if I'm given a point that is not in the first or fourth quadrant, because my calculator just can't give me that angle. So it's going to be a simple adjustment, but you got to pay attention to what quadrant you're working in so you know when to use it. So here's an example where this is going to come up. I have this point, -1, negative root 3 in the rectangular coordinate system. Since the x and y coordinates are both negative, that means I'm in the third quadrant, so that bottom left quadrant. And so when I use tangent inverse to solve here, I am not going to get the angle in the third quadrant. I'm going to get the reflection of it in the first quadrant. Okay, so if we start by just plugging in the formula, so our y value over our x value gives us root 3. And so solving this for theta, I would have theta equals tangent inverse of root 3. My calculator will give me pi over 3 for that. And so I'm going to add pi to reflect it back down to the third quadrant, which gives me an angle of 4 pi over 3. And then plugging in the x and the y to the formula for the radius, I would end up with a radius of 2 from simplifying that. So I end up with a point 2, 4 pi over 3. And it's never a bad idea to double check to make sure that you're at least in the right quadrant when you're doing this. So this one is 4 pi over 3. That is going to put me in the third quadrant where my point was in the rectangular coordinate system. Okay, so I've got a couple of more examples with this to give you some practice. I gave you another one in the third quadrant, so you get a little bit more practice with making that adjustment of adding pi for the rectangular to polar coordinates. And the last thing, I just want to end this section with some graphing. In the notes that go along with this video, you can see all of these formulas that show you the different types of equations or graphs you get depending on what the equation looks like. And so I highly recommend you plugging in some values for A and B and playing around with this to see what you get for each. And I'll do a couple with you right now just to get an idea of how to graph in Desmos in polar coordinates, because it does work out quite nice. For instance, if I just do r equals 5, and I got to zoom out here because I was zoomed in before, I get a perfect circle, which makes sense because r equals 5, that's saying the radius is always 5. So for all angles, I get a radius of 5. If I start doing something like adding trig functions, and I have to use theta here, so it knows I'm in rectangular, and I can literally just type in the word theta, and it will switch it. And I get something, believe it or not, this is not a circle. It's got some flat sides on it. Let me add some coefficients to make it look different. This is what we would call a limacon, where it has this little loop-de-loop here in the middle. I have that. If the value is, let me try to play around here. I'm just throwing different things in here. If it's just a dimple like this, instead of a full loop inside, then that's a cardioid. And then we can really start to have fun with these if I start doing things like using e to the theta. And if I start zooming out, I get a spiral here. And then the last one we haven't looked at were the rose curves. And so if I have something like a number times sine or cosine of theta, that will give me a rose. So let's try one of those before we leave off for today. So sine of 5, let's just do theta. And now it's very tiny. I got to zoom back in here. That gave me a circle. I need a number here. So let's do 3. And there's my rose curve. I get some nice petals on here when I start throwing in coefficients with the theta. And the number of petals is going to depend on the value here. So let's double it, and I get a whole bigger one there. So really have fun with this. Start playing around with the numbers so you can get a sense of what these graphs look like.